The James Webb Space Telescope, JWST, is humankind's most recent vast eye, connecting across unbelievable distances and catching light that has ventured for more than 13 billion years. This light, however, lets us know something beyond a story of time. It uncovers the development of our universe, formed and extended by its continuous expansion. As we peer back at the most far-off galaxies, we are practically seeing an ancient time, moving increasingly close to the initiation of the universe, the Big Bang. The theory of how things came to be, a basic story of modern cosmology, strongly proposes that our universe had a distinct start and is limited in age. Yet from its beginning, this solitary, enormous beginning has been met with distrust and challenges to its legitimacy, which endure even in standard cosmology. For a really long time, the theory of the universe's origin held strong, particularly after the discovery of the cosmic microwave background, CMB, in the 1960s. This background radiation, a weak, comprehensive murmur across the universe, adjusted perfectly with expectations of a hot, thick early universe. Anyway, historic observations by the JWST have recently cast doubt and raised new questions about the Big Bang's authenticity. Through the amazing clarity of the JWST, NASA's inestimable time machine, we've seen clusters of ancient galaxies far bigger and more numerous than anticipated, challenging our understanding of the universe's earliest stages. As the telescope peers back to when the first galaxies formed, it offers humankind an extraordinary view, one that the Hubble telescope couldn't fully access. Hubble was just not sensitive enough to detect the incredibly faint redshifted light of these earliest galaxies. However, with JWST's best-in-class capabilities, we're looking as far as possible back, extremely close to time itself. As we venture into this obscure domain, we encounter a well-established mystery. How did the first galaxies genuinely form? And does the universe, as far as we know it, truly have a singular, conclusive beginning? Was it a hot, misty spot so thick that light itself couldn't freely travel? This implies that, regardless of how powerful our telescopes are, we can't observe any further back with light. However, we are not limited to light alone. New technological advancements are paving the way for the detection of gravitational waves from colliding black holes, which could act as a new path to peer back into the universe's origin, perhaps even into the very singularity we call the Big Bang. The foundations of the theory of the Big Bang, and its growing suspicion, stretch back to the 1920s and 30s when cosmologists first observed that distant galaxies seemed to be receding from us. This discovery, combined with Albert Einstein's theory of general relativity, set the stage for the Big Bang model. Einstein's equations predicted that a static universe would be unstable, requiring either contraction or expansion. Seeing this expansion suggested that galaxies were once much closer together, pointing to a violent start for the universe. The universe's expansion has several significant implications. Not only do objects move farther apart, but the light produced from them stretches, shifting to longer wavelengths over time. Since wavelength corresponds to energy, with shorter wavelengths being more energetic, this redshift means the universe has been cooling as it ages. By rewinding this grandiose expansion, we arrive at a point where everything would have been so hot and dense that neutral atoms couldn't exist, leading to a uniform, searing hot glow. This glow was confirmed in 1964 when astronomers Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, an unavoidable radiation field faintly echoing the universe's fiery beginning. Yet, as the JWST pushes the limits of vast perception, researchers are finding features in the early universe that strain the conventional Big Bang story. We see huge glowing galaxies where there should be none, grouping in ways that surprise everyone. So, if the Big Bang theory alone doesn't explain these anomalies, what else could? At the heart of the theory of how things came to be lies a singularity, a point of infinite density and temperature where the laws of physics break down. This is where space and time seemingly begin. However, this concept, while compelling, has limitations. Imagine attempting to describe the whole of existence compacted into an infinitely dense point. This is where our understanding reaches a stopping point. Although many aspects of the Big Bang model have been supported by observations and lab experiments, this singularity remains a puzzle, posing the question: might the universe have had a different kind of start? In its journey to unravel the universe, science has found ways to replicate similar conditions. For example, quark-gluon plasma has been created in laboratories, and matter-antimatter pairs have been produced to align with early universe expectations. Through these tests, and by analyzing changes in the cosmic microwave background, we have a well-supported picture of the universe's evolution. However, huge mysteries remain. For instance, if all regions of space were once packed into a single point, why do we observe such uniformity in the universe's temperature? According to conventional models, areas of space should show varying temperatures since they could never have had the chance to exchange energy or information. Moreover, we would expect to find remnants from the hottest moments, such as magnetic monopoles or spatial anomalies, but none are observed. These discrepancies open the door to more possibilities. Either the universe intrinsically had these balanced properties from the beginning, or there was some mechanism that imposed these conditions. One candidate explanation is inflation, an incredibly rapid expansion hypothesized to have occurred before the Big Bang itself. On December 7, 1979, physicist Alan Guth proposed this revolutionary idea. He theorized that, before the hot Big Bang, the universe underwent an extraordinary expansion. This inflationary stage could explain why the universe appears flat, homogeneous, and isotropic. After expansion, the universe would shift into the hot, dense state associated with the Big Bang, paving the way for galaxies, stars, and planets to form. However, as researchers now acknowledge, even inflation doesn't resolve every anomaly. For instance, historical observations by the JWST have uncovered surprisingly large galaxies from the universe's infancy, suggesting a rate of expansion that doesn't quite match the predictions. Still, JWST's incredible abilities offer humankind an unparalleled view into the universe. This $1 billion infrared telescope has captured stunning images of the early universe, revealing a variety of huge, radiant galaxies from when the universe was just a fraction of its current age. While astronomers once believed they had a solid understanding of how matter coalesces to form the first galaxies, JWST's discoveries are forcing us to rethink our knowledge. Stars and systems, the JWST discoveries propose a substantially faster development than expected. These perceptions have blended energy and wariness among researchers, as certain scholars are constrained to return to basic suppositions about universe development. As per astrophysicist Erica Nelson, enormous worlds saw inside the initial 500 million years of infinite history that oppose existing models. The JWST's primer discoveries show that universes in this early epoch might be undeniably more significant and various than recently suspected, possibly lodging masses tantamount to the present huge worlds like the Milky Way. This rapid development challenges current cosmological models, which suggest that a system of such size wouldn't form until 1 to 2 billion years after the Big Bang. Nelson's examination proposes universes might develop more forcefully than expected, prompting the chance of new hypothetical structures for cosmic development. Dark matter, an imperceptible and puzzling substance, is believed to make up about 85% of the universe's mass, shaping the large-scale design of the universe. That's what traditional cosmology recommends. Worlds form inside gigantic coronas of dark matter, which gravitationally attract normal matter, permitting stars and systems to coalesce. Yet, JWST perceptions challenge this model, as cosmic systems seem to be forming in ways that challenge our comprehension of dark matter distribution. The presence of dark energy, a similarly slippery force responsible for the universe's accelerated expansion, further confounds the image. Some models suggest that early dark energy, a temporary lift in dark energy density, might have sped up universe development, possibly lining up with JWST discoveries. Anyway, such changes should accommodate with the more extensive system of the standard cosmological model, which has effectively explained astronomical development for large scales. As convincing as the Big Bang hypothesis is, it's not the only explanation for the universe's origins. A few elective speculations have gained attention, each offering unique viewpoints. The steady-state hypothesis, unlike the Big Bang, suggests a universe without a beginning, where matter continuously appears as the universe grows. This hypothesis proposes that as worlds move apart, new matter is produced, preserving a uniform density. However, it neglected to represent the cosmic microwave background, CMB, which unequivocally upholds a hot, thick early universe. The mirror universe hypothesis, a more speculative idea, places that two universes were born in the Big Bang, one moving forward in time and the other in reverse. This twin universe would develop backward, providing a mirror impression of our own. Although highly speculative, it proposes that the universe could be more complex than previously envisioned. The digital simulation hypothesis raises the possibility that our universe is a simulation created by an advanced civilization. Quantum entanglement and the specific nature of space-time lend credibility to the idea. Despite the fact that it remains unprovable, the simulation theory addresses questions of fate and reality, testing how we might understand existence. The multiverse hypothesis, a well-known alternative, suggests an infinite number of universes, each with its own physical laws. According to this model, dark energy fluctuations trigger multiple Big Bang-like events, creating a vast multiverse while our universe expands, creating a void of dark energy. This model suggests a continuous pattern of creation, destruction, and birth. Each of these hypotheses offers exceptional insights into cosmic origins, raising new questions about the nature of space-time and matter. While the theory of the Big Bang remains the leading explanation, it has been tested and reshaped by new evidence and perspectives. The JWST, with its unmatched sensitivity, is poised to unlock even more secrets of the early universe. What it uncovers may ultimately reshape how we understand the universe, pushing us closer to unraveling the mysteries of space and time. As the James Webb Space Telescope, JWST, continues to investigate the farthest reaches of the universe, it has ignited new conversations about the true essence of the universe's beginnings. One of the critical questions that remain is whether the Big Bang truly marks the beginning of everything, or whether it is part of a more complex cosmic history. While the telescope's abilities allow us to peer further into the past than ever before, there is a growing recognition that some of the discoveries made by the JWST challenge current models and offer tempting possibilities for alternative explanations. Among the most significant challenges to the traditional Big Bang model is the rapid development of massive galaxies in the early universe. The JWST has uncovered enormous galaxies forming within the first few 100 million years after the Big Bang, far sooner than anticipated. In the conventional view of cosmology, galaxies should have required billions of years to accumulate the necessary mass and become so large. The JWST discoveries suggest that the processes responsible for galaxy formation were far more efficient than current models had predicted. This raises the question of whether there are unknown factors at play that led to the rapid gathering of these early structures. Some researchers believe that this accelerated development may be linked to the presence of dark matter and dark energy, which continue to evade direct observation but are believed to influence the formation of galaxies and other astronomical structures. Dark matter is thought to form halos around galaxies, helping to attract normal matter through gravity and allowing stars to form. However, the surprising presence of massive galaxies in the early universe has led scientists to consider whether dark matter behaved differently than previously expected. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, might have played a role in shaping the conditions that allowed these galaxies to form at an accelerated rate. In addition, the new data from the JWST has prompted cosmologists to reconsider the role of black holes in early galaxy formation. Supermassive black holes, which were once believed to only form after galaxies had already developed, have been detected in the centers of some of these ancient galaxies. This discovery suggests that black holes may have played a significant role in the rapid development of galaxies in the early universe, possibly helping to drive their growth and shape their structures. If this is the case, it could change our understanding of how galaxies and their central black holes are intertwined in the vast timeline of the universe. Furthermore, as researchers continue to analyze the data from the JWST, some are considering the possibility that the universe underwent a series of rapid, repeating events rather than a single, linear expansion. This idea aligns with the theory of cyclic cosmology, which suggests that the universe goes through an eternal cycle of birth, death, and rebirth. In this framework, the Big Bang is not a unique event, but one of many cycles of expansion and contraction. Each cycle would be marked by the creation of new galaxies, stars, and planets, followed by the eventual collapse of the universe, only for another cycle to begin. This idea would require a significant shift in how we understand the universe's origins and could provide an alternative explanation for some of the anomalies seen in the JWST data. Another possibility is that the early universe may have been governed by different physical laws than those we observe today. The current understanding of physics, based on the Standard Model and general relativity, works well for the conditions of the present universe. However, as scientists study the universe's infancy, they are discovering that the laws of physics may have operated differently when the universe was in its early stages. This could help explain some of the puzzling features observed by the JWST, such as the rapid formation of galaxies and the unusual distribution of matter in the early universe. If the laws of physics were different at that time, the Standard Model may need to be modified to account for these early conditions. The implications of these new discoveries are not just academic. They could significantly reshape how we understand humanity's place in the universe. The mysteries surrounding the beginning of the universe, the role of dark matter and dark energy, and the formation of galaxies are fundamental questions that could provide profound insights into the nature of existence. As current theories are refined and new models emerge, they may help answer questions that have been posed by scholars and researchers for centuries. The future of cosmology is set to be shaped by the continued work of the JWST and other space telescopes that are being developed. As technology advances and new data is gathered, researchers may begin to uncover even more astounding revelations that challenge the way we think about the universe. Whether these discoveries lead to the confirmation of the Big Bang hypothesis or the development of entirely new cosmological models, they will undoubtedly expand our understanding of the universe's origins and evolution. The journey to uncover the true story of the universe is just beginning, and the answers we uncover may forever change how we view the universe and our place within it.